Hello, and welcome to this video on the electric field due to multiple charges. In this video, we're just going to take a look at a very common occurrence that in real-world situations, you have more than one charge. And so, up until now, we've only talked about the electric field due to a single point charge. We're now going to figure out what to do for this very real-world case where you have multiple charges. So let's think about it a little bit. If we had multiple charges, we can draw a couple. We can put maybe, I don't know, a positive charge, say, over here. And we can put another one over here. We know that each of these charges is going to create a field, so I might use some different colors. In fact, so let's make that guy a blue one. So each charge is going to create a field. Remember, the field points in the direction that a positive charge would move, so it's going to move away from this one. So this charge wants to do something like this in terms of its field. And of course, this other charge has a similar sort of field. They're the same size of charge, so we'll pretend they're both 1 coulomb. Then the lengths of these arrows should be the same. And then further out, they might be smaller and doing something like that. Roughly speaking, something like that. Now, the trouble, of course, arises because these things will start to overlap. So I'm going to draw in similar extensions of that one. We can see that some of them start to cross, and the question becomes, what should we do? Well, remember that the field is nothing more than basically the force divided through by the test charge that we used to measure the force. And we certainly know what to do if we have multiple forces. Forces are vectors, they add like vectors, and then you get a net force. So it should come as no surprise, really, that what we're going to do here is add these individual things. So each field will have an effect on the test particle. If one of this one would want to push it that way, the blue one is trying to push it that way while the yellow is trying to push it that way. So that's two vectors that are resulting in forces, really. So we have to add them. Okay? So the fields have to add, and the fields are vector quantities, so they must add like vectors. Okay, this is the idea of superposition, and what it amounts to is very much what we've just said. We're going to add those vectors. So close in, right, this yellow one is maybe contributing a very small bit. So it would subtract a tiny bit from the blue, but not much. So here the blue is going to pretty much dominate. And if we track it through, when we add here, right, these vectors will cancel in their horizontal components, but their vertical components will add. And so we can track that field line. That's going to do that sort of thing. Okay, and this one's going to do the same sort, approaching, but not quite intersecting. All right, so we can start seeing what's happening. Basically, the field on the far side is mostly doing what the one charge wanted. It's unaffected by the other one, because by here, the blue one is really weak. In the middle, they're sort of doing this weird kind of dance of being forced away. And things like that. Now that diagram is getting messy, so we look at this one, and on this one you can see exactly what I'm trying to do here in this diagram. This is the result of actually adding up vectors carefully calculated through the computer, and you can see that this pattern that I was trying to draw is what happens. So on either side, the forces, or the fields rather, from each individual one are just sort of the important thing. On this side, it was the blue, and on this side, it was the yellow. But now we've got them combining in this way and giving rise to this nice pattern, where in the middle, right between them, there is no field, and then just above and below, you've got the vertical components combining to give you fields that push you straight up and down, and so on. Now notice in this diagram, there's some very cool features, and these are going to be true in general for all of any kind of electric field that you're going to draw. So the field lines in this diagram, which we've drawn in just tangent to all the vectors, these things will always start at a positive charge and end at a negative charge. Okay. They will always indicate something about the charge ratio of these objects. So if I had more charge on one of the particles that I was considering, then that should have more lines coming out of it. So the number of lines that are coming out of that thing indicates something about the charge. The one with more lines coming out of it is the higher charge. They also, of course, indicate the field strength, as we talked about in the video on field lines. They have to indicate that field strength, so where it's dense, the field is strong, and where it's less dense, the field is not as strong. And these are drawn such that the tangent, again, as I said, the tangent to the field line is the electric field at that point. And notice what I was trying to do in my drawing and what I've done correctly in this nice diagram is that the field lines can never cross. If they were to cross, what would that mean? Well, if we go back to our original drawing, you can see here the individual vectors from the field, so the blue vector and the yellow vector, those certainly cross, that's clear. When we add those things as vectors, that results in one net direction. We cannot possibly end up with sort of two net directions.